Yes. So, all right. So we haven't missed too much. We're, yeah, just first little introduction we missed, but now we go back to the presentation, which is really right at the beginning. And so we have
Thank
not
you.
lost too much altogether. You're welcome. Thanks for stopping me there. Okay, let me go back to my presentation.
Thank you.
This one. There we go. And uh, right. Okay. All right. So I was saying, with GAP, you can visualize groundwater data, upload and view your own data, create your own predictive maps, which is something that's very unique to this platform in particular, this modeling functionality, which is basically a simpler way of creating the maps that we have otherwise done offline. And as you're doing with Inca, sharing data with others publicly. And of course, you can do this with models as well. And now looking at some of the functionality of the platform, when you first go into the GIS part of it, you're probably not logged in, which you would see up here in the upper right. You get the option to register if you don't have an account yet, or to log in. But you can tell right away if you're logged in or not based on the number of windows or icons on the left here. So the first one is just for public layers, and which gives you access to the layers that we have already loaded on here. So that would be some of our collected groundwater quality data points, but also our maps. So we have lots of different maps, global, regional scale maps that we've created. And down below these initial gap layers are some of the parameters that we use in modeling geogenic contaminants. Now, these are not the only ones that you can use, but these are some of the more typical ones. And so we have them available on here to make it easier, in particular, well, to compare your data against, or compare whatever data against some of these parameters, but also to use these parameters later in creating a model, if that's what you ultimately do. So these other layers is from this category of geology, climate, and population. Those are from other sources, and then we have those referenced of what the actual source is, but they're publicly available data sets. So you can navigate around with all of those different layers. When you do put data points or any data on the GIS site, but whether it be a raster or point data, you can access more information about this data by clicking on this eye icon in the upper right, and then clicking on the feature or that part of the map that you're interested in, and get information. So in this case, in this example, it says feature info arsenic points. That's just the name of the database. And then get this shows actually all of the data, all the different columns of the data that were uploaded. So when you think about uploading a table, a spreadsheet of, let's say, arsenic and fluoride data points, anything that you have in any of those columns will ultimately could be displayed here in this window. So you don't see it automatically, but when thinking about when you're uploading your data points to GAP, whatever you have in those columns is what's ultimately visible. And when you share that data layer, all of that's going to be visible. So you want to think about what you actually want to show. Maybe you don't want to list all of the rows. Maybe there are too many. Maybe they're not all needed. Maybe some are just for internal use or whatever. But anyway, when you click on this icon, and then you get crosshairs, you click on the point to find out more about it. Each one of these points here represents the data, the information in a different column from that spreadsheet, from that CSV file. So, yeah, you can always go back and redo things, but anyway, I just want to make that point that that's really sharing all of this information that you've uploaded. And okay, so I'd already talked about some of the publicly available layers. including now the shared layers below. I didn't mention those yet. That's where the Inca points come in that are on the website right now, and some other examples of other people who have shared data, including from Pakistan. UNICEF has their own arsenic maps, for example. And well, let me just go back here, mentioning the base layers in the upper right. When you click on this globe icon, we have 5 different base layers that you can choose from. So anyway, that's pretty clear, I think, to toggle among those different options. And this is just an example of bringing up a few different maps that we've created. So of all of arsenic, but from separate studies. So from Pakistan, from Southeast Asia, from China, and the other layer shown on here would be metamorphic rocks. That's one of the publicly available layers of the geology. And so I don't know if well, just let me mention this right now. You can change the order in which the different layers are displayed. So, if you have point data and raster data, if you want to see both, you have to put the point data on top of the raster data. You do that when you hover over the layer that you want to move. A couple of, there's a pop-up and there's an arrow up or down, and you can easily move the layers that way. Another useful feature here in just displaying and viewing the different layers is to adjust the transparency. So here, as we can see, there is some transparency to all of these maps. But if we look at the middle of China, for example, we can see some of the rivers and some of the labels, the names of cities behind, and that's doesn't come up by default. When you adjust the transparency of a layer, you can see this. So this, it's like any other GIS system, but it's anyway, that functionality is here too. And one of the simplest ways of exporting, I'd say exporting a map, but really exporting a picture, is to click on the print icon, and you can adjust the map to this highlighted area, and then click submit, and a PDF is produced and downloaded. And then it comes out looking like this, showing the legends of the different layers that you had on the map, on the GIS, when you printed this picture. And here, okay, this slide's again more about the shared layers, the publicly shared layers. So that's where your Inca data are. This again was an example from UNICEF of their own arsenic map. So you can compare that to the arsenic maps that we've produced, for example. And your data, this was an older slide, so I think this was from 2017, if I'm not mistaken. I think now on the site, or you have on the site, 2017, 2020. And so yeah, that's fantastic. Here I just want to make a point of what the modeling capability is of GAP. So at the left is this China map, arsenic map predicting arsenic in groundwater in China, that took about, it was an overall study of collecting all the data and doing the work, was took about 2 years, and that was with offline programming and everything. But we were able to recreate the same map with GAP, with the modeling tool in GAP, which is really pretty simple, or I would say simplified. You don't have as many options on GAP, but for that it's easier to use. It's simpler, and despite that, we're able to produce essentially the same map. I mean, if you look at them side by side, it's, aside from some differences in the actual colors themselves, the patterns are all really there. And this was, we had an intern who was a bachelor's student work on this, and she was able to produce this in about 5 days. Once learning where everything goes and collecting the right data and getting it uploaded, was still able to produce almost the same map, which we thought was quite remarkable. So this slide is just about to say that GAP can be used for things other than groundwater. And I assume everyone right now is interested mainly in groundwater quality, but again, you can use this. You can use this for other things. Lately, we've had a study on aquifer vulnerability, and for this, we were using not measurements of arsenic or fluoride, but rather using, in this case, we're actually using tritium in groundwater and using that as an indication of recent recharge, and from that, look considering how vulnerable the aquifer is to pollution. But in terms of this modeling or even mapping, it doesn't matter. There's no real big difference. We're still looking at essentially a geographical, realm or an issue, and different measurements at different points. So whether that's arsenic in arsenic concentration or tritium concentration, we even had there was someone after who worked on this with a problem with soil. I had given a workshop on using GAP in Africa some years ago, and one of the PhD students attending said, "Yeah, you know what? This is interesting, but I'm working on soil contamination, but I could still do this because she had soil samples from different places in the field, and in this case, it was cyanide in soil from small-scale gold mining." And was able to use GAP to create a prediction map for cyanide pollution in her field area. So just as some examples of how else you can use this for topics beyond or other than groundwater contamination. We've also looked at contaminants in food like arsenic and rice, which is not such a big diversion from arsenic and groundwater, but it's still a pretty interesting topic. That's something that for us it's totally undeveloped at this point still. This could also be used for nitrate or micropollutants, trace elements in soil, for example, too.
Sorry, a question.
Yes.
Do you use the same platform, or is it in another one? Because when you enter in GAP Maps, there are another platforms, doesn't it?
Well, yeah, we have, it's all in the same platform, this interface where I was showing, it's the same exact place. It still says groundwater assessment, but it doesn't matter. It could be soil assessment. Because ultimately you're uploading a table of some georeferenced measurements. And so it's up to you just to keep track of what it is you're uploading and how you label it too. I mean, it could be soil, cyanide in soil, whatever units. But no, it works the exact same way. Okay, so I hope that answers your question. But
yes, thank you.
okay. And so this is an example of using this directly GAP for aquifer vulnerability. And this was just a very like a proof of concept little exercise to see if we could, how well this would work for things other than groundwater quality. And so these points just represent are coming out of a study that was already published years before assessing aquifer vulnerability, in this case, in the plains of Canada. So that's Alberta and Saskatchewan, I think. Anyway, each one of these points they looked at, I think it was depth to groundwater and basically the thickness of the sediments between the water table and the surface. And based on that, we came up with this index of aquifer vulnerability from 1 to 4. And so we took that scale of 1 to 4 as our target variable. So we were modeling not arsenic concentration or something, but modeling this aquifer vulnerability index from 1 to 4, and just to see, could we use, find the right predictor variables of maps and of things like soil type or precipitation or anything like this to recreate this pattern that is seen in these points. And the answer is yes, we could. So this was modeling showing the probability of any given pixel or part of the map exceeding this aquifer vulnerability index of 1. I mean, it's kind of arbitrary in choosing what index to model. But the point is, when you look at this, you see the same basic patterns coming out on the right as on the left. And for this, we used aridity, clay content, precipitation, and slope. And these are all publicly available data layers, actually available at a global scale. Many, or I think actually all of which we have on GAP. But even if one of these layers is not on GAP, you can upload that for your study area. You can upload it as a raster and then use that in modeling, for example. And that's what was done with that China study. All of the layers that were used there were not necessarily already on GAP, and so that student had to upload those. But once she got them into the system, use them, under her account, use those as predictor variables to create that model. On the left, that was that example I mentioned from Burkina Faso. I said Africa, was from Burkina Faso about gold mining, and she published that too, which is really nice. On the right represents a little kind of internal study we did on predicting copper concentrations in subsoil in Europe. There's a very large data set that's available that we used, and we were able to create, come up with some good results. This is all on GAP directly. So that was, I guess, something of an introduction. I have some slides now about just getting set up with GAP and using it. Let me quickly plug in my computer before it goes out. I think I made it. My battery is going down. And right, so with GAP, if you haven't already done this, in the upper right of the screen, it looks the picture looks different. This page looks different now, but the functionality in the upper right stays the same. To register, and once you're registered, then you can work with your own data. And of course, you have to come up with a password, accept the terms and conditions and all this. But once you're logged in, then you see on the left more functionality. Because if you remember before, when you're not logged in and just using it anonymously, there are only 2 icons, and then there are 5 once you're logged in. And so the main ones are my layers. So that's your data that you upload, whether that be point data, raster data, or feature data, say from a shapefile. Statistical analysis, that's working with those data. And then communities, that's where you're sharing the data with just like a few people. So as you've done with Inca, you've shared it publicly, and that's easy. I mean, that's great, but then everyone sees it. Communities, you can get a little more specific, and you say, I want to share it with like 5 different users. You add them to a group, and then you share a layer with that and with that community, and then everyone sees it at once. That's what that function is about. And the bottom left, it shows the layers that have been shared with you. So you can, when you're sharing a layer, obviously you could share it publicly with one of these communities or with an individual user. And so the shared layers function shows the layers that are being shared with you.
A question about
Yes.
that does everyone in the community has to be registered, or
Yeah.
or yes? Okay.
Yeah, that's how it works. When you set up a community, you basically start typing in the username or email address that they're registered under, and then it'll usually you type in a few letters, it'll pop up, you click on add, and they're in that community. But yeah, I mean, that's the only way to really, it's not like, it's all in an internal system. So we're not using like Google or something to, connect with someone that way. It's all, they have to be registered on GAP in order for that to work. But it's really useful if you have a relatively small number of people where you're working with data that you don't necessarily want to share publicly, then this is what that's for. Okay. Visualize your own data. Okay, so right, this is an example from UNHCR. They had a data set of boreholes in Africa, and we had helped them upload this. And so it's just, this could be any data set, but right, you can This is just about displaying those data. That's pretty clear, I think. You can set up the legend, the color scales. So for this example, depth greater or less than 50 meters, but that's totally up to you what kind of threshold you set, how you label this, what colors you use, what sort of icon, whether it be a dot or a square or a star or something like that, how big. So there's quite like any GIS actually, there's quite a bit of flexibility in that. And yeah, this is an important part of the platform are the help pages. You can either get to it directly from the help menu at the top, or link is what it is, but also from any of the windows that you might be working with, there will be a question mark in the upper right. And when you click on that, that will link to open up in a web browser, the associated help page for that particular area. And I mean, there are, a lot of there's some tricky bits sometimes to getting data formatted properly, particularly CSV, tabular data, getting that properly formatted before it will actually upload. By that I mean it's like if there are certain special characters that aren't accepted, and so anyway, the help pages we try to outline what the rules are. So if you're getting stuck on something, you should check there first to see, okay, if it says don't use this, that, or the other, then that should help clear up those problems. I mean, I don't remember it myself actually what all the different issues are, so sometimes I have to go back and forth. So it's can be a little bit tricky, but once you have it right, then it works. It uploads, and then it's on the platform. So anyway, the help can be useful, really useful for getting past any problems like that. And yeah, it comes up in a separate web browser. It's in this wiki format. Right, so I tried to describe everything. It's been a little while since I worked on this, so I can't promise that every last thing is described perfectly. I don't think anyone ever can, but I tried to anyway to get at least the most important information on here, so that the help is indeed helpful. Yeah, and there's a little bit about uploading and displaying data. So here are some points, some general points I want to make about getting your data ready. And so I think this is particularly useful for you if you're going to be uploading points, well, uploading data to the platform for one, but let's say doing anything with these data, or maybe modeling with them later. So first point, it's important to inspect your data before beginning any modeling. And I would say before even just sharing it, just look at it closely, visualize it, look at minimums and minimum and maximum values of the data that you're reporting, whatever measurements they are. And so you may have, let's say, arsenic concentration, fluoride concentration, pH, electrical conductivity, and then maybe some other, some major ions and dates, when the measurements were taken, or depth of the well, or depth to the water table. It's good to check each of those columns. So before looking at uploading this to anything, I think in, let's say, Excel or whatever, but most likely Excel, probably looking at all this data, it's good to like sort each column one at a time. And this is how I do it, and I'm sure there are other ways, but sort from minimum to maximum values, and just look at them just to see, is there anything that really doesn't make sense, negative values that for a parameter where there is no such thing as a negative value. I mean, these things can creep up. It also often highlights where you might have a blank space entered in with a number. So as soon as that happens, that number is no longer interpreted as a number, but interpreted as text, because you've introduced a text character, a blank space, which may not at all be obvious when you just glance over the data. and that'll of course cause a problem later. It won't be interpretable if it's text and not a number. So anyway, there's always things like this, and the more data you have, and from the more different sources and different campaigns and things are pieced together, the more likely it is, almost certain it is, that you'll have some issues like that. And it's better. My point is, it's better to look at this beforehand rather than later when you're trying to use those data in a program like GAP, because then it's not always obvious where the problem is. And eventually you'll find it and say, oh, there was a blank space in there that didn't belong, or there was a negative value. Oh, I could have figured that out beforehand and saved myself all this trouble. So that's my point with that. And that's the second point on this slide too. Correct, and then the third point, correct any anomalies, typos, text characters where numbers are expected. Yeah, these are just all the things that come up. The last one here, plot the numerical and geographical distribution of your data. This can be done in GAP. Yeah, this is important. So the first part, the first 3 points are just looking at typos, basically, or total errors. And the last one is to really just get a sense of better understand your data and how they're geographically distributed, which you cannot at all tell by just looking at an Excel table. I mean, you could look at latitude and longitude, but to see how everything lies in relation to everything else, you plot it on the map, and then that's really good to do that. Again, to acquaint yourself with the data before you go to any of the subsequent steps. It's tempting to just say, okay, here are the data, we throw them in and go to the next thing and try to do everything really quickly. And then something doesn't work and you're not sure why, and that can be frustrating. So it's good to kind of do this slowly, which is in the end is faster than trying to do everything really quickly and having to go back and correct a whole bunch of mistakes and realize that things don't quite make sense. So that was that. So what the statistical modeling looks like in GAP, this comes under the statistical analysis section. We go to I show here on the right hand side. There's the data tab. Once you get your data set up there, you can go to models. But the basic idea here is to combine your data with any data that you've uploaded with spatially continuous data as predictor data. This could be either your own data that you upload or the data that we already have on GAP. So that's those are basically your options, and or not. You can the possibilities. With GAP, if you're going to be, with the way we have this modeling set up, we're always going to be modeling point data as a target. So the idea when I talk about modeling, modeling means a whole bunch of different things, but it's really this statistical modeling, this geographical, or say geostatistical modeling based on point data that have been, that represent actual measurements of one sort or another. So let's say arsenic concentrations. So that's the thing. That's the first piece you start with. So that's what you already have, right? You measured that. The modeling has all to do with trying to create a map out of those points. So it creates this spatially continuous data set, a map from these points, which normally would be done through interpolation. I mean, let's say traditionally would be done through interpolation, maybe extrapolation. And if you have a lot of data points, they'll often work, work pretty well. But it just has to do with the geographical distribution of the different points, and doesn't consider at all the processes behind them about why do you have high concentrations here and low somewhere else. And that's something that we get at with this modeling, this machine learning modeling, where the parameters that we're using are not just the geographical distribution of the points, but rather what values do those different points have in different parameters. So what's the geology like? What's the soil like? What's the climate, topography, and so forth? What is that like in these different places? And with geogenic contaminants, a lot of these, we can actually predict the geogenic contaminants really well based on these sorts of parameters. I mean, it makes sense, right? Geogenic geology, which is all natural, so we know it's based on and the hydrogeology with the geochemistry, and there are many different layers that either relate, I would say, directly or indirectly to the geochemical processes that are involved in causing these contaminants these geogenic contaminants to accumulate. Now, a point that's often brought up is, well, how can you use these maps of surface parameters to create a model of groundwater quality when the groundwater is by definition in the ground, not at the surface, and might be at some really great depth. So really far removed from these parameters that you're using at the surface. And that's a totally valid critique or question, because there is this physical disconnect between the surface and some depth. But it turns out that what we see at the surface is often closely related to what we find at depth. And I say often, not always, of course, but it is actually the geology, is what we see on the surface is often at the same at depth. Well, things like topography play a really big role, where we see if there's a steep slope or not. If there's a gradual slope, the groundwater will tend, we can assume in general, the groundwater will flow more slowly. Contaminants can have a chance to accumulate. Many of the soil parameters that we've used in modeling are also very strong, or they perform very well, even though they're measuring, representing some parameter within the top, let's say meter or a meter and a half of the surface. It often works really well for modeling the groundwater the groundwater quality. Now, all that said, our models are not perfect. I mean, and they're kind of far from it, but still quite good. And I think this is a big reason for it. Because of this disconnect, but the fact is, we only have data that are at the map data at the surface. Now, if you have something like 3D geology or geophysics, then you could maybe get closer to modeling it, using parameters that are really close to what you're actually trying to model, the target of groundwater quality. So that works. In the end, this works quite well. Now, what we have also done, just as an aside, is sometimes we'll create models where we'll model with some of the in situ data that were measured with, let's say, arsenic concentrations. So maybe measuring it with oxygen, the oxygen concentration or pH or something else. Now, we can never make a map out of that, because those parameters that we're using are also just point data, right? But you can still create a model to find a strong statistical relationship. And oftentimes when we use those sorts of data that are measured directly with the same sample, groundwater sample, then we can create really strong, really great maps, that are much more accurate than the ones that let's say considerably more accurate than the ones that we use to create maps with. And that's just a function of these predictor variables, these data that we have available. So this comes down to, if you're going to do any of this sort of statistical modeling, what is the purpose of it? Is the purpose to look at processes and, what other constituents might have a role or have an influence on your target variable, like arsenic or fluoride? Then you could probably just model with point data. And that should still work in GAP, actually, too. You'll get the statistics, and you'll find out which variables are most important and how they relate to your target variable, though you cannot create a map out of it. If the goal is to create a map, then you have to basically use maps as input data, as the variables. So hopefully that was at least somewhat clear. just want to explain that a bit because that's a very important point about basically like what this modeling is about, why we do it, and how it should be done. And I mean, this slide right here is just showing how to start doing this process in GAP, but there are other ways of doing this as well. I mean, I've typically modeled in done this by programming in R, the statistical programming language, but the basic ideas are the same between either one. Now, I think here I think I'm trying to remember what these slides are, but just going through some of the steps of creating a modeling table. So we were in the statistical analysis section of GAP, and on the left is the statistical analysis. On the tab on this window is data. And then you have options to add, remove, edit, so forth, a data table. Now, what a data table is, this is what you're going to be using for any kind of data analysis, whether it be here or in, let's say, R. It's just basically, you could think of it kind of like as a spreadsheet. You know, you have rows and columns, essentially. It's a matrix, right? So you'll have like a row for every data point, and the columns might be something like latitude, longitude, concentration of the target variable, maybe depth, whatever other things you measured, the depth, the pH, electrical conductivity, things like that. But you have to construct this as a first step before you can actually use those data. And that's what this is about here. So we go to add, you come up with a table here, edit. Let me just go back one there. So it was statistical analysis, data, add, and so we added a row here, added a data table, and then we want to populate that data table, and this data table by going to the edit button. And that brings up this next like pop-up where you can then choose by checking these boxes the different parameters you want to add to your data. I think I may have left out one little step in here, and that was including your actual point data, which you've already is what you would have already have had to upload. And this stage, it's adding the different checking the different basically maps that are either in GAP, there's the public layers, or your own maps that you've uploaded, from which you want to extract the values for your points that will go into this data table. So in this example, you want to extract the values of potential evapotranspiration, of precipitation, sand in the subsoil, for example. And then once you've gone through those steps, or you've checked those, click on, I think it's add. I think just trying to move my little Zoom bar out of the way so I can see the whole slide. Then up here is add to table, and then then GAP goes to each one of these rasters and each one of these maps, takes your data points, the X and Y coordinates, picks up the values and puts them into this data table. That's what all that is about. All right, so select column is where you add select column is where you add your target variable. As I mentioned, check all the boxes for the maps you want to get data from, add to table, and this is the result. So it just shows for each of the different data parameters, give some basic statistics, minimum and maximum values, the mean, standard deviation. This is also what I was mentioning before about looking closely at your data, just understand them before trying to jump ahead too quickly to subsequent steps. And here we actually have some color coding to highlight any problems. Green means everything is okay, and that's what we see right here. But for example, if the minimum and the maximum of any given parameter are the same, then they'll come up red, because if there's no variability, if the minimum and maximum is the same, that means all the values have the same exact value. So it's a constant, and it you can tell not you cannot use that to predict something else because it doesn't vary at all itself. If that comes up, the row here will show up in red, and so that's useful. Or you want to remove that variable in that case to make sure you don't use it because it's pointless. Going back to the statistical analysis section, we have a descriptive statistics area. Also lets you visualize your data when you can see what the cumulative distribution is, and you can put things in like the mean and the median. Just ways of better understanding your data actually. So yeah, I think that was the end of this initial presentation. Let me stop sharing my screen for a second if I can. Oh, I think it's hidden, but there we go. Let me stop sharing this for a second. Now, yeah, are there any questions? I mean, actually, let me say this. I have another presentation lined up that goes more into the modeling, but I'm not really sure that's what you need or want, but maybe it is. So I think, if you can give me some feedback of what you want to do in this second half, we could, for example, just look at GAP and getting data prepared or uploading, something like that. Or if you're pretty interested in the modeling, I can go ahead with that and talk more about that part. So what do you guys think?
I have a question regarding the parameters. I understand that arsenic and fluoride are the main focus, right? But is it possible to, or do you have some examples about other contaminants? Because not only groundwater contaminants, but even, for instance, microbiological parameters. So, could you share some example of maybe if there's already a map regarding other parameters?
Yeah. I have some of those actually. Let me it's actually in this other presentation, but let me just share that right now. And yeah, it's always easier to look at a picture, right? So do you see that about nitrate? Or maybe no?
Yes.
Okay. So this is in a presentation about modeling, this other kind of the introduction about this spatial modeling. So yeah, absolutely, you can model other things. So we have not really done it yet with nitrate, but these are some examples from, I guess, fairly recent examples. So there's one from the US, from the USGS from a couple of years ago now, using these basic methods of modeling nitrate in groundwater. From 2016, Ouedraogo in Burkina Faso had made this model of all of Africa based on the points shown here. Again, nitrate in groundwater. And then also a couple years ago, this group worked on nitrate in India. The next slide I have on here, let's see, I think showing more different scales. That's all arsenic, but the next one, your other groundwater applications. So here in the upper left is Erickson et al. This was also a USGS group, and they were modeling redox conditions in these northern, I think, glacially affected sediments in the US. Radon in Germany, the radon in groundwater. So from China, iodine and fluoride. Manganese, so going back to the USGS example, with that same study, they looked at manganese. Now we have two actually in Southeast Asia recently. We published a paper looking at manganese and iron and comparing both of those to arsenic. which is actually really interesting because in these reducing environments in Southeast Asia where the arsenic is, quite prevalent in deltaic areas, oftentimes we found, or you'll find high manganese concentrations immediately adjacent to the arsenic, but not in the same exact location. And that has to do with just the redox scale and what and some at some level of at some level the manganese will come out and will get dissolved, and if you move further along the redox scale, you'll come to the arsenic. So the interesting point then, what we made with that was that although arsenic is fairly well understood, or let's say aware of in Southeast Asia, there are also problems with manganese, which cause ailments and things, but not to the same extent that arsenic does, but it's still a health concern. But it could very well be that people or communities that are using wells, that they say, okay, well, the arsenic is not a problem here. It could be, based on what we know of the region, but our well is fine with arsenic. They might still have a problem with manganese. So that was, I think quite useful there. Here in the lower left, another example of nitrate in California, and they did this in a 3D sense. I would say in a quasi 3D. I'm pretty sure they used depth information from individual wells and created a whole bunch of different depth slices and then just pieced them together. So not a true 3D model. Fluoride, arsenic. Yeah, okay, so some more of the same here. But also you mentioned biological contaminants, and that's something that I was looking at before with this other organization that had actually started in this direction and kind of got sidetracked or stalled, or the funding led them one way or often a different direction. But they published a study a few years ago in ES&T about just correlations between different I think fecal coliforms or E. coli and different parameters, to try these kinds of parameters, like things like land use and population density, but probably also precipitation, topography. It's a lot of the same parameters that we use for geogenic contaminants, and found strong correlations. And so the next step was to create such models for biological contamination, but we didn't get to it. And it's something that's, I think, totally doable and would be relatively easy to do. Just haven't gotten around to it. Is there anything else that you were curious about that you might be interested in doing?
Yeah, it's very interesting. Thank you for sharing.
Hey, you're welcome. All right, let me stop that sharing again.
Thank you very much, Joel, for your nice presentation. It was really, really nice. Thank you very much. I'm really interested in the way you are modeling and predicting the behavior of the contaminants during time. So which kind of algorithms or models you are using based on the data you have?
Mm-hmm.
Could you please share us a little bit more about this? Or
sure. If you know what, so that is all covered actually in this other presentation I have. So it might be good just to go through that. If that's, I mean, just based on these two comments, I think that's good. You're interested in the modeling. Good. I have that lined up.
Okay, Joel.
Just go to that. And I think
thank you.
That a lot. So, share. And let me just go to the beginning. All right, so this is from last year, but okay. Yeah, so I'll get to the algorithms and all that, but just for a little bit of background, what is machine learning? It's really not that fancy, as fancy as it might sound initially. It's really just statistical learning or statistics that's using the advantages of a computer to run calculations really quickly. It's really what it's mainly about. I think I would copy something here from ChatGPT. Just, I mean, not that I actually use this that much, but it's a subset. So machine learning is a subset of artificial intelligence. It focuses on development of algorithms and statistical models. So again, it's all about statistics, which are really quite old and, you know, are being done before, you know, we had these modern computers that allow computers to learn and improve their performance on a specific task without being explicitly programmed. Fundamental idea behind machine learning is to enable computers to learn from data, identify patterns, and make decisions or predictions based on that learned knowledge. Again, something in theory we could all do ourselves, but when you're looking at a lot of data, it's just it becomes untenable. It's too much, and so we use the computers for that. And I'm just trying to move. Okay. Various machine learning applications. Medical diagnosis, looking at images, you know, trying to find patterns in medical images, for example. Temperature prediction, image and speech recognition. We keep encountering this more and more in the world today, right? But it's, yeah, these are big fields. Natural language processing, recommendation systems, autonomous vehicles, which apparently are coming coming up quickly. Financial modeling. Let's see, and spatial prediction modeling. So this stuff that I'm working with. So these are two examples of 2017, 2018, arsenic in Pakistan and fluoride in India. And the basic concept, which I've already described earlier today now, but this might help to understand it a little bit better. Especially having the different images. So the idea on the left is we start off with concentration data where we have points where we know the geographical location, latitude, longitude, and also it's the measurement that we've made in that location. And in case you don't recognize this right away, this happens to be East Africa, so Ethiopia, Kenya, and Tanzania, but looking at fluoride concentrations. And then comes in this geostatistical modeling, but actually I would say probably better to say machine learning modeling, because we're not doing just like we're not just interpolating. We're actually finding values from different data sets. So things like like climate and soil and geology, and adding them to this data table that I was mentioning before, and then running one algorithm or another to produce a model. And the model at first is just a statistical relationship that you can't really visualize so well, actually. And there are different ways of understanding it. And one way of using it is to apply that model, which is just, basically, you think of it as like a formula saying if you have this much of this value and this so much of the other value, then we're going to say that, you're going to have high fluoride or not. You can apply that model that's at this point just existing in memory in the computer to these data layers like the climate and soil and whatnot, and then produce this prediction map. In this case, it's a binary map or a probability map of a binary variable saying what's the probability of an area here in East Africa exceeding in this case, WHO guideline of 1.5 milligrams per liter of fluoride in drinking water, groundwater. Good reason for using a binary variable is that's a lot easier to model than by doing an actual regression. To try to model a continuous variable, you could say, well, it'd be nice to know, do we have 1.6 milligrams per liter? Do we have 5? Do we have 10? I mean, yeah, of course, that'd be really great to know. But the reality is it's really, really hard to model when we're going back to the point I was making before. If we're using the surface data to model something at depth, I mean, there's too much of a disconnect there that when you try doing a regression model, it's usually pretty inaccurate. And in the end, it doesn't matter all that much, depending on the use or the target or the purpose of creating the map. In this case, we're looking at a health-based guideline of 1.5 milligrams per liter. Obviously, if you're consuming water with 1.5, or let's say 10 milligrams per liter, it's a lot worse than consuming water at 1.5 milligrams per liter. So, I mean, that's true, but technically it's all an issue and should be resolved. And so one of the points of creating such a map is to identify where more follow-up work needs to take place. And where to actually go back and say, and to identify, okay, we really need to be measuring more in these dark brown areas, because there's a really high probability of having high fluoride in those areas, rather than, let's say, just doing a blanket study of a whole area, a whole country, not just blind, not knowing in advance what you might find, because presumably you can't test everywhere simultaneously, right? Just there aren't the resources to go around. So this kind of a map helps you target places to go to help you better identify the resources, and actually also to more quickly find the places where there is a real problem and then do something about it, whether that be switching water sources and introducing some kind of a filter or whatever. But the map here is really meant to be an intermediate step to get to actual solutions. So for that reason, looking at probability of a binary variable is really quite good. It's easier, it's more practical on the one hand from the modeling perspective, and on the other hand, it's also, it serves its purpose for identifying where more work needs to take place. And this just is a little bit more about, I guess, what I've already been saying. We're taking our input data, combining this with some spatially continuous predictor variables, and I've made the point about why they need to be spatially continuous if you want to create a map in the end. But also the question about how do we do this? So there are many different ways. Initially, what we did in some of our earlier studies was using logistic regression, which is represented here. And there are others too, but this is technically machine learning. People don't often think of it that way, but it actually is. It's like basic, multiple linear regression, but for a binary variable. That's the logistic part of the name, and the output is not an actual, it's not an actual prediction of the concentration, but rather a probability of exceeding some threshold of being, in this case, of having a value of 1 versus 0. That's what the logistic refers to too. The binary data set gets recoded as being 1s and 0s. So with the example from the previous slide, everything above 1.5 milligrams per liter would get recoded as a 1, and everything up to and below and up to 1.5 milligrams per liter fluoride would get recoded as a 0. And so that's just going into the math of this. We're looking at the binary variable. What's the probability of getting the 1 or the 0? And those 1s and 0s are determined by you, of where you set that threshold to define something as being high or low. And for things like fluoride and arsenic and other contaminants, it's a pretty obvious choice is to use the health-based guideline, saying, everything up until some concentration is reasonably safe. Everything beyond that is problematic. And so that's an obvious cutoff to take. I'll get more to on a future slide. I'll get to some more of how those algorithms work. I think in between now, I just have some examples of some other examples. This is one that's in review right now. I mentioned this before of modeling aquifer vulnerability based on tritium. Part of the reason I had this in before is I was doing this at the IAEA, which deals with a lot with tritium and isotopes. But the idea is the same. We're measuring a binary variable, high or low, and this is showing a probability in the end. Probability of high tritium which in this case we're interpreting to mean that the aquifers in the groundwater in those areas are more vulnerable. This was and then these were the slides that we were just looking at, other examples of nitrates, of this one of different scales. So I'd mentioned before, we've modeled globally, and this group from the USGS some years ago modeled the whole US for arsenic, and before that did New England. Coming on 20 years ago, gosh, 18 years. Showed this example before from us from China. This is an earlier one of Southeast Asia, all arsenic. And here in the Red River Delta of Vietnam, using 3D geology from a lot of different boreholes, different depth slices were created. Though in the end, actually, the overall results or the maps were not that much better than the initial map based fully on surface data, actually. This one, we looked at all the different examples, or some of the different examples of things that you can model, or different groundwater quality parameters that can be modeled. I think, okay, here's an important point where I get to give some of my opinion, I guess. Identifying the modeling goal and choosing an appropriate modeling framework. So this is an initial step of this process. So to first ask yourself this question before going to the next stage. It doesn't need to take much time, but consider what you're creating the model for. What's its purpose? How should it be used once it's created? And what data are available? I mean, that comes from a practical side. So I'd mentioned this a little bit before. What is the purpose? Is the purpose to create a map? You know, a prediction map to help highlight where more testing should take place, or to maybe just to get an overall view of the groundwater contamination in a whole region or country? Or is it maybe to figure out what processes are at work? And that could be using some of these spatially continuous variables like climate, for example, but you might also want it to use point-based data that will help you nail that down better. But again, if you use any point-based data in a model, you cannot create a map out of that. So that's a little bit of a trade-off. So all of these things to determine the type of model to use and how to process the data. So it's important to be clear about this first before going to subsequent steps. So arsenic, as an example, arsenic in groundwater is relevant for health when consumed as drinking water. Therefore, relevant health-based threshold can be useful as a modeling target to later communicate to authorities. Again, thinking about how should this be used after you've created it. So from our experience, these maps have been really useful for authorities to take up the information. I mean, much better than some report saying, oh yeah, 67% of the wells exceed some threshold. This, when it's kind of, people's eyes kind of glaze over and all this, but a really nice, a well-produced map goes a long way to communicating information, or at least attracting attention and then getting people to ask more questions. So that's an important thing to keep in mind. Now we're going back a little bit to what sort of possibilities are there in this machine learning modeling. So initially there's a split between, and there are probably other ways of breaking this down, but this is one way anyway. There's a split between unsupervised and supervised learning. So unsupervised is for grouping and interpreting data based only on the input data without any sort of input from you about how things should be grouped. I myself have never really used this. I haven't had the reason. It hasn't been necessary, but rather all of these other examples come into the category of supervised learning. So developing a predictive model based on both the input and output data. So input data, input would be the different parameters like the geology and soil, all these different, the environmental parameters. The output would be like the target data. What do you want to get out of this? The target of this would be the arsenic or fluoride concentration. So that's how it's supervised. We say we have all these parameters that we think say something about what the groundwater quality is going to be, but we know for a fact that we have these concentrations at these points. What's the connection? That's really the question. So out of the supervised learning, as I mentioned actually already, there are two basic ways to go about this. One is to deal with classification or with regression. So regression is looking at a continuous variable, and as I mentioned, this can be really difficult to do well based on the data that we have available, and for that reason, we usually go to classification. And so that just means looking at different classes. And of the examples I've given already, there are two classes. I was looking at only two classes, high and low, based on some arbitrary threshold or a threshold that you set. However, you can model more than two classes. You can model 3 or 4 or 5 or however many, but the more you get, the more classes you introduce, the more it becomes like a regression. And so it's becomes more difficult, actually, the more that you add, and sometimes less meaningful. I usually find it's easier to just model a binary variable and then look at maybe different ranges of probabilities that the model shows. So you could color code the map as 0 to 20%, 20, 40, 40, 60, and so forth, to give you an idea of how great of a chance is there that we're exceeding this one particular guideline value, for example. Right. And so, okay, so here are some examples of different modeling algorithms. So traditional methods, I guess, this is probably fair to say, traditional. Linear regression, using a continuous variable, or logistic regression, which is using a binary variable. We did all of our work initially with logistic regression. Lately, we've been using tree-based methods, in particular random forest. And so there's a trade-off here with the tree-based methods. They usually perform better, and because they're really good at, they perform better because they're good at nonlinear problems. But because of this, they're harder to interpret. So they produce a better result, but you have to go through a few more steps to better understand why the model works as it does. With looking at something like a linear regression or logistic regression, you can in a very straightforward way interpret the model by actually just looking at the coefficients of the different variables. So of the different input variables, you get a magnitude and a sign, basically, of every coefficient. So right away you can see, is there a positive relationship or a negative relationship or a correlation? The more precipitation, the lower the arsenic concentration, for example. And then so that's the first thing to look at, is there positive? What's the sign of the coefficient, a plus or a minus? And then after that, what's the magnitude of that? Is it a little bit positive or a lot positive, for example? This is assuming you've scaled all of your data beforehand so that you can compare the coefficients with each other in such a manner, but it's totally doable. And so for that reason, these linear methods are considered to be very interpretable. The tree-based methods, also artificial neural networks, support vector machines, and any host of a number of machine learning methods out there now are more difficult to interpret, but there are still ways of doing it. And so I don't let that stand in my way, because I think we can still learn a lot from these methods, despite the fact that they're not as straightforward as the linear methods. So I already kind of talked about logistic regression, actually. So it's predicting a binary variable, and the output is a probability. Really, from the output, it varies from 0 to 1. So 0%, 100%. It's quite easy to use. I'll talk a little bit more about random forest, because that's what we've used a lot, and actually works really well. Usually when I've tried other methods, other tree-based methods, but also support vector machines, and neural networks, I've never had gotten a performance, a model that has performed quite as well as the random forest, and it also runs a bit faster than generally runs, faster than the other methods. So it's kind of the go-to method for, at least for these sorts of problems. With other sorts of machine learning problems in different fields, they have their other kind of go-to methods. For this, random forest works really well. I mean, I've seen this, from our own experience, and also read this from reports from other people. So the way this works is it's an average of decision trees. So a decision tree is the building block of this, and that is just saying, if you don't know what a decision tree is, see if I can explain it. Saying trying to break down a target variable based on various conditions. So we're looking at, let's say, high or low arsenic, and do we have what precipitation level of precipitation do we say, if for example, is that going to split the data set into high or low arsenic? And it's never going to be perfect, so therefore we have different layers of this, different splits to this tree. But basically it works by taking a variable, deciding at what threshold of that variable, like precipitation, will that, say if it's below, I don't know, 500 millimeters a year, then it will give low, there's more likely have low arsenic, and if it's above 500 millimeters per year, it'll have high arsenic. And it doesn't, again, it's not going to split it perfectly. It might be like 60-40 or something like this. And then it goes to the next stage. So and then in each one of these sub nodes, you take some other variable and try to better split the data between your target variable between high and low, like high arsenic and low arsenic. And so you can grow these trees to all these different branches and nodes for as deep as you want. And a decision tree, actually, if you just take one decision tree, you can divide this data up really, really well. But the problem with that is that it becomes overfitting. So you can really well describe a given data set, but then you can't use that single decision tree to generalize to unseen data. That's the real big criticism or drawback of just using a decision tree. So what a random forest does is it combines a whole bunch of different trees, decision trees, and therefore the name forest. So it's a forest of trees. And each one of these trees is grown in a different way. And it's grown in a different way by looking at different data. So that means, on the one hand, it uses different subset of the input data, and in a random sense. So this is also this is where the name random comes from. So you have a random forest. It will take a different subset of the input data to create a given decision tree with. And then at each one of these branches, each one of these nodes, as you go down to split up the data, it won't consider all of the predictor variables you give it at once. You'll only consider a subset of those. Maybe like say if you give it 12 variables, it might look at only 3 or 4. And those, which 3 or 4, that's decided randomly. So each one of these trees is grown by looking at fundamentally, different numbers, different data, all coming from the initial data that you give it, but in a different way. And by doing this, by creating many, like let's say 1,000 different trees, and then averaging the results, that actually works a lot better than a single decision tree, because it's seen different combinations of these data, and that means it's better to generalize to unseen data better than a single decision tree. So it's really all about avoiding overfitting and creating something that you can use to generalize to unseen data, which is the whole point of doing any of this modeling in the first place. And I don't really know of anyone using decision trees to create a prediction map. I mean, I just don't hear about it. But random forest or any of these other tree-based methods are all about this, about growing these trees, these decision trees in different ways, combining the results to produce a single output that is your model. So I think, yeah, I've described that. But the last point here is variable importance and partial dependence plots. So let me go back. So, okay, so the problem with all of this, of growing all these trees and having all these different layers or different nodes and branches, I mean, you're not going to go back and look at each one of these 1,000 trees and say, oh, well, do I see a pattern here, or how can I link these things up? It becomes too much, right? So the way to interpret the model, to understand why it works as it does, even it works well, but kind of want to understand why too. There are a couple of different ways of doing it. One is looking at variable importance, and the other one, common ways. Another one is looking at, there are others too. The other one is looking at partial dependence plots. And what I show right here is a partial dependence plot of aridity versus some prediction. So this is the prediction on the y-axis. So something like 40%, 45%, 0.4, 0.45 is the probability of exceeding whatever threshold was used in the binary model. And on the x-axis, we're looking at the different variables of aridity. So between, let's say, 0.5 and 1.25, we see quite a big jump. And well, I mean, there's a clear jump. There is an increase that means saying that the higher the aridity, the greater the chances of exceeding the threshold of whatever it was, like fluoride in groundwater. So this is one way of understanding how the variables interact with the model, or what effect do they have, what the relationship do they have with the target variable. The other is the variable importance. And I don't think I have maybe I don't have a plot of it right here, but it's really just a number. So it doesn't matter too much. But what it means is it's a way of objectively analyzing the importance of all of the different input variables, the predictor variables on the output. And the way it basically works is it takes each variable one by one, randomly scrambles its value. So if you think back in that data table, you have rows and columns, and if you take a column, take the column of a given predictor, and take all those values in the different rows and just scramble them, and so that you have the wrong values. The values are all in the wrong place for the given row, and then rerun the model, and then the importance is judged by how much the model, how much more poorly the model performs. So the idea is, how important was it that you had all those values right in the first place? If you scramble those values of precipitations or aridity, and the model suddenly a lot worse, oh wow, that was a really important variable. But on the other hand, if you scramble those values of like precipitation, rerun the model, and the value doesn't really change, or the performance of the model doesn't really change, it predicts just as well as it did before, you say, well, what good is it having that predictor there? Because even if I use completely wrong values, it doesn't change the model at all. So that all comes down to saying, okay, that variable has very low importance. And so you can then rank these. You can assign a number, you calculate, there are a couple of different ways, but anyway, you have a scale. You can see which variables are more important than others, and by how much. And that's one of the other ways of analyzing how well the different predictor variables work. So data preparation, I already talked, I think, a lot about this. Except I'll make the point again that it takes up most of the effort in all this modeling. The actual running the algorithm, once you have everything set up, doesn't take that long. If for the kind of things we're talking about, it's maybe a couple minutes or something, depending on how much data you have. But usually a lot quicker than that even. So I say it's an iterative process. It may be necessary to repeatedly modify your data over the course of modeling, and that just comes from seeing, okay, maybe we're not, the model isn't performing as well as we would like it to. What are we missing? For example, that will then motivate you to go back and look at this a little bit more closely. Maybe, you take some kind of make some kind of data derivative of something you already have. So for example, you could look at distance to rivers. And this would be something you'd make in a GIS program. You can run one of the functions in there to create a map of plotting the distance to some some features like the lines of rivers. And then you say, well, we'll try 200 meters, we'll try half a kilometer or 2 kilometers, something like that. So those are all these different. When you start getting into it, you realize there are all these different possibilities of things you can try, and that's why this sort of becomes an iterative process. Two basic categories of data, right? The target and the predictor, right? I've already talked about that enough, I think. Point data, bring all data into a single file, like a CSV with Excel, right? I already talked about it. Yes.
That's a question. When you check the data, do you use like the similar scales, or
depends?
Okay.
I mean, like you in general, it's good practice to normalize all of the data so that, let's say, they all vary between 0 and 1. But with the tree-based methods, it doesn't matter.
Okay.
Some other ones do, like with support vector machines, they work in a really different way. They look at like distance in model space between different points, and so the scale should be the same of all variables. But it's an extra step. But for the tree-based methods and actually for the linear ones, it doesn't matter. So I don't bother with it. I mean, because the model results will be exactly the same for those types of models. So, but yeah, it is a consideration, but you don't always have to do it.
Okay.
Yep.
Thanks.
Welcome. Now let's see how far I want to go here, because I have to leave right at in 20 minutes, which I think is 10 o'clock by you. And I think this presentation would go on for quite a while. So I'll keep going until you ask more questions, and I'll answer them. But just to let you know, in 20 minutes we have to close off. But so let's just say, ask me any questions, and maybe while you're thinking of them, I'll keep going, but interrupt me and stop me at any time. If that sounds good. All right. I don't know if I need to spend much time on this. This is kind of specific, using tritium for this model in Africa, in West Africa. No, I don't need to go into that. Spatially continuous data. Okay, these are some good general points for sure. Always plot your data, ensure that the map covers your entire area of interest. For example, the model domain, i.e. the model domain. Right, so let's say you want to model all of Mexico, but I mean, so basically every variable that you would put into a model would have to be of a map that covers the entire country. Because if you cut off the Yucatan Peninsula, for example, for whatever reason, your map isn't continuous, that means that even if it's just one variable and that variable is in the model, your output map in the end is going to miss that section. So just good to be aware of that. Look critically at the range of values contained within the data set. Do the values vary considerably? Do they do so where you have point data? This is actually pretty good. It kind of goes back to the point that I showed in GAP, where we had the color indication if there's any variability in your data or not. If for all of your data points, if the value is the same, it would be saying, well, that variable doesn't do you any good. But here, does the value vary considerably? So, particularly if you're not looking at a really wide area, broad area, you might take some of these predictors and find that there's hardly any variability at all, particularly in climate. Let's say you're in some pretty flat open area, some small catchment or something where precipitation doesn't vary that much. It's about the same everywhere. then it's probably not going to be a good variable. It maybe okay, it's a continuous scale, it varies a little bit, but you don't see these great big variations. So you can think about this beforehand, before waiting to have the model tell you that it doesn't that variable doesn't do you much good, and say, does that make sense at all? I mean, can I expect to understand variability in groundwater quality based on this given variable? Another good example, I think, is geology. If it's all in the same basic geological setting, then that's probably not going to be a good variable. But if there are big differences, if you have these big contexts between metamorphic and sedimentary rocks, and let's say you're really more detailed geological maps, and then probably that would be really good. I mean, that would be a really good variable to use. But if that's not the case, then you probably don't even need to use it in the first place. But this also helps you, just identify what sorts of variables to seek out. And it becomes more challenging the smaller the area becomes. So again, like country scale, you usually find all the variability for a country like Mexico. It's big enough, right? There's a lot of variability in everything. But if you're looking at a really small region, it might not, things in the environment might not change that much. And maybe it's all the same topography as well. So I've seen people do this using limited number of data in a small area, and say, well, you know what, how do you expect to model this at all by this method? Because all the predictors you're trying to use have basically the same values throughout your whole model domain, or throughout, for all of your data points. So it's something that's sometimes overlooked, and so therefore I mention it. Check the spatial resolution of each data set. Is the resolution appropriate for the scale at which you want to model? Right, because a lot of data sets will be, particularly on a global scale, will be very coarse. So maybe even like 1 degree of resolution, and maybe on a global scale it's fine, but maybe the area that you're trying to model falls within 1 degree of latitude and longitude, and so you can't use that. So it's something to consider. Other different resolutions among your raster files. This is not a problem, but it's more of just a practical consideration. So it just means that before you can ultimately create a map, you will have to rescale or resample the coarser data sets to match the resolution, the pixel resolution, the data resolution of the finer data sets. You're not creating or losing any information. You're just reformatting the files so that you can use them in the end. But really, it's fine to use. If you have 30 arc-second resolution climate and 7.5 arc resolution soil data, totally fine. You just need to reformat the in this case the climate data to merge with the soil data later. Now these are just examples from this Tritium model. Really not that important, other than just to see what kind of variables I used. So really from climate, topography, soil, geology. Right, but it doesn't matter so much otherwise. Well, here's another important general point with model verification. So you've created a model, produced a map, put pretty colors on it, but how good is it? Yeah, so how do you test this? How do you know if it's good? Because you can always produce a model, but then you need to decide is it worth using? How much can you trust it? So even if a model even if a model perfectly predicts the input data, it may not work well on new data, which is overfitting, which is like the example I gave of a decision tree versus random forest, which circumvents this problem through that algorithm. And it's essential to evaluate model performance on different data. A couple of ways of doing this. I have always just taken the original input data, like of arsenic concentrations, and taken a subset of that off to the side, modeled with the majority of the data, like let's say 80% of the data, created a model with that, and then tested that model on that 20% of the data that did not go into the modeling process itself. And then typically what you do is that you repeat this process many times by randomly dividing the data set into a training set and a testing data set. So you would let's say you do this 100 times. At the beginning of each step, you randomly split up the data into, let's say, 80% training, 20% testing. You create a model, train a model based on the 80% of data from what you're calling a training data set, produce a model, and then make predictions for each one of the points in the test data set, which is or validation data set, is comparing what the prediction is to what the actual value is. And there you can generate various statistics to analyze and consider how accurate the model is and how well it performs. So some examples. So ones you would have otherwise heard of for regression, using modeling a continuous target variable. Things like mean squared error, root mean squared error, mean absolute error, or coefficient of determination. However, none of these work on these are for a continuous variable and not for a binary variable. So for a binary variable, which is all these maps, these examples I've shown so far, you're looking at things called true positives, positive and negative predictions, and whether those are true or false. So you hear about true positive, false negatives, false positives, true negatives, and then there are different ways of dividing up these statistics of these numbers, of comparing them to each other to produce various statistics like accuracy, sensitivity, and specificity, which sound like the same thing basically, but they're not. Sensitivity is the accuracy of, it's the accuracy of how many of the positive cases got correctly classified. Specificity is for negative values. How many of the negative cases got correctly classified? And some of this terminology, in case you're interested, comes from the medical fields, because these sorts of statistics are often used for predicting diseases. And so for them in the medical field, oftentimes it made sense to use one word or another, but that's kind of where a lot of this terminology comes from. Balanced accuracy is one that I think is much more important than accuracy, because they go, accuracy, you want to know how good the model is, right? That seems kind of straightforward just to choose that. Not necessarily, and I'll give you a quick example. If you have a data set with only 5% of high cases, and this often comes up in, again, the medical field, where you have, most of the cases you look at, there's no disease. You're looking for cancer or something like this. It is a common example. But just a few cases have the disease, or let's say high arsenic in groundwater, then you could come up with a really, really accurate model by saying, well, the arsenic doesn't occur or the cancer doesn't occur in any of the cases. And then you would have an accuracy of something like 95%, because you got them all, you got 95% of them right by just saying that the high cases don't exist at all. Because in the by and large, they don't exist, right? So that's just, it can be very deceptive then to only report an accuracy value. Therefore, it's necessary to look at things like sensitivity, specificity. How many of the high values do you get right? How many low values do you get right? The balanced accuracy is the average of both of those. So that example I just gave of like 5% high cases, that's, in the end, pretty hard to model with these methods. So ideally, you'll have a balanced data set. Let's say 50%, perfect is having 50% high, 50% low, like 50% above WHO guideline, 10 micrograms per liter, whatever, and the other half below it. Of course, you're never going to, in general, it's not going to just happen on your data set, but you always want to look at it and say, okay, well, if I'm going to pick this threshold, because this threshold makes sense, because, from guideline values, whatever, how does that balance the data set? Sometimes you're lucky and you don't have to do anything. It's like, oh, it's almost 50%. And I can go on to the next step. In other cases, it might be like 30-70 or 25-75, 20-80. then like I've done things where then I've downsampled the majority class, like let's say it's 80% low cases. I've just taken a random subsample of those to match the size of the positive cases, which were like 20% of the whole data set, and then modeled those together. And then in the next iteration, I picked another different random subsample and did it with, and then from the minority class, and so it works better. It doesn't bias the model toward that majority class. And so after each iteration, I record the results and then average them in the end. So on this screen, there are some on the slide. There are some other things, like some other statistics that are not as important. So I won't go into them, but just to that there are different ways of dividing all of this up. Here was an example of what false, negative, true, positive, what some of this means. So just taking 12 samples and looking at an actual classification, ones for 1 through 8, and then zeros from 9 to 12. That's what the original data show. Let's say from a validation test data set, and then you, let's say, produced a model with the training data, and then created predictions for each one of these 12 data points, these data rows. And then down here, the result is just comparing what the prediction is against the actual classification. So here it's a false negative because the prediction was negative. It was saying we're predicting 0 instead of 1. So that's negative, but it's false because it was incorrect. It was actually 1. It should have been 0. True positive, we predicted 1 and it was 1, so it's true. False positive is the opposite of what I showed in here at the beginning, or in case 1, but here in case 9, positive because we're predicting positive, but the actual was 0, so it's false. And the other possibility is a true negative. You're predicting something that's negative, and oh, look, it is actually true. It should be negative. And maybe I'll just finish off with this slide and stop there. But yeah, it's just a little bit more to describe about this. Just for reference, this is this chart, looking between predicted cases and actual cases. That is known as a confusion matrix. And why confusion? I'm not sure. I mean, it is confusing, maybe, but I actually can't tell you why. But in case you get into this and you come upon the term confusion matrix, that's what this is. And it's really just comparing the cases of comparing the results to reality, looking at true positives, false negatives, false positives, true negatives. So here, this is starting with the predicted condition. Positive means we're saying that it's high for a binary variable, negative if it's low, and then comparing this to the actual condition. Was the positive condition, does that does that correspond to reality? Then it's true, and so forth. So what are we showing here? I'm not sure what 8 plus 4, of the actual condition. Yeah, okay, so like I said, the cancer is often used as an example because this comes from the medical field. So yeah, let me just stop there, because otherwise it's kind of, it'll take too much time actually. But it's just kind of, other statistics just build on this basic concept of true and false, positives and negatives when we're dealing with a binary data set. And there are different ways of combining these numbers to produce different statistics, and those are the things that you see reported in papers, and different ways that you can analyze and compare your models from one to the other. So yeah, let me stop there with the presentation. So yeah, I hope it's been interesting. We have time, I think, for at least one question. If you have one right now, let me know.
I have one question.
Sure, please, yeah.
That's related to the use of your maps. If you have, for example, longitudinal data, so in over time you use like how the geographical distribution or the changes of heat zones are changing over time, and like in a video or something like that, do you use that kind of things, or just like, well, this is happening this time, and then
Yeah, well, with the geogenic contaminants, I mean, we've just assumed, I mean, that's not always true, of course, that it's a snapshot, or it's basically a long-term average of what's happened, and it's not changing that much, so no. That's usually a function of the data that we have available. So we're working right now, for example, on nitrate in Switzerland, where we have a lot of data. Hopefully, we'll be getting a lot of data with a lot of time series data, and then we can start looking at changes in time. And I think what we would, what we would do is create different maps for different periods of time, like on a yearly basis, and then be able to see how patterns may change. With these a lot of them, the examples I showed, we just had maybe one data point from every well, and so that's all you have, right? But the more data you have, the more possibilities that arise, the more you can do with it.
Do you think that because a friend of us use, for example, for it's not like predictive analysis, but like planning scenarios, like if you are going to in this pattern of behavior, human behavior or industrial behavior or anything, the pollution is going to this way, so this is going to happen in 30 years, for instance. And if you do this kind of take these measures, then this is going to be the scenario. So that could be done with machine learning or so.
Yeah, I mean, it all depends on the data that you have available. So if you can predict existing patterns with some data set, and you have because you have that relationship, and you say you produce a good model, you can take scenarios of how that one predictor changes with time, of how you expect it could change in time, like one would be like CO2 emissions or whatever, temperature change, anything that might change in the future. And then if that you use those different values in that variable and apply that to the model that you created. There is a danger, of course, that you might be making predictions for areas of values in that variable that that did not go into the original model. So that would be a consideration, right? But if you've actually been able to, if you have there are cases of, let's say, more extreme values or of values that you expect things to go in the future, if those are already, if some of those, at least some of those are present at now, where you can compare with actual validation data, then maybe then you can use create scenarios of anticipated changes in whatever that predictor is for the future.
Thank you.
Welcome.
Joel, I just wanted to say thank you, really. It's very interesting. This is really the state of the art about it. So we really appreciate your time. And we would like to stay in touch regarding the specific projects we have. So we really appreciate your time. It was really fantastic.
Great.
Thank you very much.
You're welcome. You're welcome. Yeah. And if you have any questions about anything I talked about, whatever, feel free to email me. But otherwise, let's stay in touch. And I mean, I know there have been times in the past where maybe I've been slow to respond or whatever, but let's stay in touch. All right. Thank you.
Thank you so much.
You're welcome. Have a good day, everyone. Take care. Bye.
Thank you very much.
Welcome. Bye.
Thank you.
Welcome.